Alright, so for today's lesson we're going to cover factoring. We're going to factor our trinomials ax squared plus bx plus c, which we've done in previous lessons, but today we're going to take a look at what happens when your a value is not 1. We have done some of these in the past, and it does rely on similar factoring techniques. So we'll start with we're going to recall the approach to factoring. Let's say something like n squared minus 3n minus 10. So what we did when we factored a trinomial where we had an a value of 1, note that the a value did not have to be written, but the 1 is implied, is that we took a look at our c value here and we said we were looking for two numbers that multiply to give us negative 10, and those same two numbers need to add to give us negative 3. So in this case, looking at our factors of negative 10, we had our options. Because it does multiply to a negative, we know that we need one positive and one negative. So our options for factors of 10 are 1 and 10, and 2 and 5. Because here we need to add up to a negative 3, we're looking for the negative number to be the larger number. So what we're going to do is we're going to assign the negative sign to the larger number. And here we see that the values that work for us are 2 and negative 5, telling us that our factored form of the expression would be n plus 2 times n minus 5. And remember, we can always FOIL to check. So today what we're going to do is we're going to take and we're going to try to factor things that require a little bit more process here. We're going to factor something like 3x squared plus 13x's plus 14. Note that we do have a 3 out in front. So what that does is that changes our approach. We can't just look for two numbers that multiply to give us c and add to b, because it's not a given that our two original values will be something simple like n and n. Instead, we're going to have a 3x and an x. And now this will change as we go forward. If we have numbers like 6 or 10 or something like 24, what we'll have is we'll have multiple options because those factors 6, 10, 24 all have multiple ways to multiply to give us those values. So what we do is we're going to take what's called the a times c method. How the a times c method works is that we're going to take our initial value, a, and we're going to multiply it by c. So in this case, 3 times 14 to give us a new number of 42. Now what that value of 42 tells us is we're going to now look for two numbers that are still going to add up to that middle value of 13, but now that multiply to give us 42. So we can try out all the factors of 42 and see which ones work for these numbers. So our factors of 42, as we try this out, my factors will be 1 and 42, 2 and 21, 3 and 14, and 6 and 7. And what we're looking to do is we're looking to multiply to a positive 42 and add up to a positive 13, so I know that my signs need to be two positives. And it looks like those numbers that will work will be 6 and 7. So in your a times c method, what I cannot do is I cannot just plug that answer in and say it's x plus 6 and x plus 7. What we're going to do is we're going to reverse our FOILing approach. We're going to take this middle value of 13x's and we're going to split up that 13x's. So that my initial problem will read as now 3x squared. We're going to split it up into plus 6x's and plus 7x's plus 14. So what I did was that initial value here in blue, in the pink, is 13x's. I ripped it apart. I uncombined my like terms. Now the reason why we're doing this is we're going to go through and we're going to find the factors that make this problem work. The order of the 6x and the 7x does not matter. But what we can do now is we have 4 terms, and that's very, very important. We have 4 terms here. So when I have a polynomial expression with 4 terms, what I can do is I can split up that 4 terms directly down the middle, and I can look for ways to factor each of those binomials on the inside. So when we're going to go through and factor with only a binomial, is we're going to look for GCF. So is there a common factor between 3x squared and 6x? Yes, they both share that common factor of 3 for the coefficients, and they both share that variable of x. And like GCF factoring from our previous section, we're going to go through and divide each of those by that factor of 3x and write what remains. So we're left with x plus 2. Okay, so what we just did was we factored our GCF from the first binomial, and we'll repeat the process and do the same thing with the second. So we'll look for something that both 7x and 14 share. It looks like 7x and 14 both share a 7. And I'll write what remains on the inside. That should be x plus 2 when I factor that out. All right, so all of our work has been done. Now it's just a matter of recognizing where our answer is. What always should happen in any one of these problems is that we should have inside, we should have a binomial expression that is the exact same in both parts. And if it's not the exact same, that might signify that we missed the GCF when we found maybe just a common factor instead of the greatest common factor. Or it might mean that simply the polynomial is not factorable. What we found with that match is we found one of the binomial factors of our problem. Now we are missing our second binomial factor, but that's just composed of our GCF. So we can put those two things together. And there we have our factored form of the original expression, 3x squared plus 13x plus 14. And in factored form, we have 3x plus 7 times x plus 2. Recall, you can always FOIL to check. All right, now we can try this out with maybe a negative sign as well, see if we can adjust our approach with the negative. So let's say we have an example of 5x squared plus 4x minus 12. We'll do the same thing. This is called your a times c method. Now for our a times c method, we're going to multiply a times c. And in this case, when I multiply a times c, I'm going to get a value of negative 60. So I'm looking for two numbers that multiply to negative 60 and add up to a b value of, in this case, 4. Now if I take and I find all my factors of negative 60, because it's a negative, I know that my signs need to be one positive and one negative. And because I have a positive 4 as my b value, I know that the bigger number needs to be my positive number. So I can try out my factors, 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, and 6 and 10. And again, I'm going to assign all of my negative values to those smaller numbers and see which one adds up to positive 4. And it looks like our last set of factors here does that. So I will now take that positive 4x and I'm going to split it up into 10x and negative 6x. Again, order does not matter when you write those two terms out. I'm choosing to put the 10x first just to illustrate a point with my negative signs later on in the problem. So from here I'm going to count out my terms, and it looks like we should always have 4 terms at this point. And it looks like we do, so I can now split my problem in half. And here's where we're going to go through and find out those GCFs. So the GCF in my first binomial is 5x. And then I'll write what's left over when I do that. So I'll divide 5x into both of those terms. 5x squared divided by 5x is x. 10x divided by 5x is 2. And repeat the process. Now note, whenever I have a negative sign here, because my goal is to match up those inside parentheses, I always want to take out a negative factor here. Something that we had mentioned previously when looking at GCFs, you always want that leading term to be positive. So I'm going to factor out my GCF here. 2 goes into both those terms, 3 goes into both those terms, but 6 is your GCF. And I'll factor it out, leaving me with x plus 2. So note that because I took out that negative sign, I was able to adjust my signs. And here we have, in the end, very important, we have our match here. With those sets of parentheses, x plus 2 is one of my binomial factors. And there we have the remainder, GCF factor, 5x minus 6. And this method, again, call our AC method. And it will work with any factorable polynomial where a does not equal 1.